Hello and welcome back. In today's video, we are overclocking the Ryzen 9 7950X 16-core CPU all the way up to 5.95 GHz using the GIGABYTE X670E Aorus Master motherboard and Eclk Quantum Custom Loop water cooling. Zen 4 offers a wide range of overclocking tools, so in this video we'll explore a wide variety of overclocking strategies. Hopefully this provides you with a solid foundation to start your own overclocking. Alright, we have a lot to do, so let's get started. The AMD Ryzen 9 7950X is part of the AMD Ryzen 7000 Zen 4 AM5 desktop processor lineup. The Zen 4 desktop CPUs, codenamed Raphael, launched on August 29, 2022 during an AMD livestream. At launch, there were 4 SKUs available, of which the Ryzen 9 7950X we are overclocking today is the flagship product. Zen 4 Raphael is very similar to Zen 3 Vermeer, but there are some noteworthy differences. Most importantly, Raphael requires the brand new AM5 socket and supports DDR5 memory. The CCDs featuring the Zen 4 CPU cores is AMD's first chip using TSMC N5 manufacturing technology. Raphael also introduces AVX 512 support and operates at significantly higher clock frequencies. The Ryzen 9 7950X has 16 cores with 32 threads and a maximum listed boost frequency of 5.7 GHz. The TDP is 170 watt and the PPT is 230 watt. In this video, we will cover 5 different overclocking strategies. First, we simply rely on AMD PBO and EXPO performance boost technologies. Second, we tune Precision Boost Overdrive with Curve Optimizer. Third, we tune Precision Boost Overdrive with Asynchronous Eclk. Fourth, we try to do a manual overclock. And lastly, we use GIGABYTE Active OC Tuner. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. Along with the AMD Ryzen 9 7950X and the GIGABYTE X670E Aorus Master motherboard, in this guide we will be using a pair of G.Skill Trident Z5 Neo DDR5 6400 memory sticks, an RTX 2080 Ti graphics card, a 512GB M.2 NVMe SSD, a Seasonic Prime 850W Platinum power supply, the Elmo Labs Easy Fan controller, the Elmo Labs EVC2 SX, and the Eclk Quantum Velocity² AM5 water block and Eclk Quantum water cooling. All this is mounted on top of our favorite open bench table V2. I explained how I use Elmo Labs products in SkatterBencher number 34. By connecting the EFC to the EVC2 device, I monitor the ambient temperature, water temperature, and fan duty cycle. I include the measurements in my Prime 95 stability test results. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees Celsius water temperature. I use this configuration for all overclocking strategies. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before starting any overclocking, we first have to check the performance at default settings. Please note that this motherboard by default has Precision Boost Overdrive enabled. So in order for us to check the performance at default settings, we first have to go into the BIOS and switch to advanced mode, enter the advanced CPU settings submenu, enter the Precision Boost Overdrive submenu, set Precision Boost Overdrive to disabled, then save and exit the BIOS. Note that the Precision Boost to Boost algorithm is still active even though we've disabled Precision Boost Overdrive. The standard parameters for Precision Boost 2 for this CPU are as follows. Here are the benchmark results at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4578 MHz with 1.123 volts. The average CPU temperature is 81.2 degrees Celsius. The ambient and water temperature is 27.3 and 37.1 degrees Celsius, and the average CPU package power is 192.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4814 MHz with 1.198 volts. The average CPU temperature is 86.1 degrees Celsius. The ambient and water temperature is 26.4 and 36.7 degrees Celsius, and the average CPU package power is 204.5 watts. Now let us try our first overclocking strategy. But before we get started, make sure to locate the clear CMOS pin headers. Shorting the clear CMOS pins will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. In our very first overclocking strategy, we simply make use of AMD exclusive features like Precision Boost Overdrive and extended profiles for overclocking. With the launch of Zen 3, AMD also introduced an improved version of Precision Boost Overdrive. That's a toolkit that allows us to manually tune some of the parameters governing the Precision Boost frequency boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the platform overclocking knobs from Zen Plus, PPT, TDC, and EDC, and the processor overclocking knobs from Zen 2, Boost Override and Scalar, Precision Boost Overdrive 2 introduces Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. AMD's stock values, which can be set by disabling PBO, the motherboard vendor values, which are programmed into the BIOS to match the motherboard VRM specification and can be set by enabling PBO, and custom values, which can be programmed by the end user. In this overclocking strategy, we're just enabling Precision Boost Overdrive, whereas in the following overclocking strategies, we'll manually tune some of the parameters. We rely on the motherboard pre-programmed PBO parameters by enabling Precision Boost Overdrive. We find that the following values have changed. For previous Ryzen CPUs, increasing the platform power parameters had a substantial impact on performance, especially for higher core count CPUs. From our Prime 95 result, we see that the CPU is operating well below the maximum temperature of 95 degrees Celsius. So we can expect some additional performance when enabling Precision Boost Overdrive. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD exclusive technology that essentially allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. Then AMD AM5 users can just enable that performance with a click of a single button, so it saves you from a lot of manual configuration work. While our memory kit is rated at DDR5 6400, I had to run it at DDR5 6000 for stability reasons, as my system wasn't stable at higher frequencies. I'm using an early CPU, an early motherboard, and an early BIOS combination, so memory overclocking is likely to improve in the near future. Upon entering the BIOS, switch to Advanced mode. Enter the Advanced CPU Settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Leave the Precision Boost Overdrive submenu. Leave the Advanced CPU Settings submenu. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set System Memory Multiplier to 60. Then save and exit the BIOS. As expected, enabling Precision Boost Overdrive provides a small performance improvement in multi-threaded applications. And in addition, thanks to enabling EXPO, we see a performance improvement of up to 6.44% in Geekbench 5. When running Prime 95 small FFTs with AVX512 enabled, the average CPU effective clock is 4729 MHz with 1.187 volts. The average CPU temperature is 95.3 degrees Celsius. The ambient and water temperature is 25.8 and 37.6 degrees Celsius, and the average CPU package power is 240.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4857 MHz with 1.236 volts. The average CPU temperature is 95 degrees Celsius. The ambient and water temperature is 26.5 and 38.5 degrees Celsius, and the average CPU package power is 238.5 watts. In our second overclocking strategy, we will use the Curve Optimizer tool included in the Precision Boost Overdrive 2 Overclockers toolkit. As I mentioned earlier in the video, Curve Optimizer is an important new feature of Precision Boost Overdrive 2. Curve Optimizer essentially allows you to adjust the factory fused voltage frequency temperature curve of every core inside your CPU. The VFT curve is a curve that defines which voltage should be used for a certain frequency at a certain temperature. The higher the frequency or the higher the operating temperature, the more voltage is needed. Curve Optimizer adjusts the VFT curve by offsetting the voltages of that factory fused VFT curve. By setting a positive curve optimizer, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative curve optimizer. You can offset the entire curve by up to 30 steps in a positive direction and up to 300 steps in a negative direction. Each step represents approximately 5 millivolt. The traditional approach for overclocking AMD Ryzen CPUs is using a negative curve optimizer setting. Two things happen when you offset the VFT curve with a negative curve optimizer setting. First, you effectively tell the CPU that it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. As I mentioned already, Curve Optimizer is available on a per core basis. And that's great, that provides us a real benefit, because some cores can overclock better than other cores. The manual tuning process with Curve Optimizer can become quite convoluted because it spans a wide range of scenarios, from single-threaded light workloads to all-core multi-threaded heavy workloads. My tuning process with this Ryzen 9 7950X was as follows. First, I use a broad tuning approach to get a big picture understanding of the tuning opportunity. Then I narrow down the per core Curve Optimizer settings to achieve stability in a light workload. Then I verify the stability in all core multi-threaded workloads. Lastly, I run through all my benchmarks to validate stability in a wide range of test scenarios. The broad tuning process includes using SuperPi32M with affinity set to a specific thread to check the maximum effective clock frequency, then gradually increasing an all-core negative curve optimizer until the point of instability, then gradually increase Fmax boost override in case the boost frequency is hitting the frequency ceiling. The narrow tuning process includes gradually increasing the per core negative curve optimizer until the point of instability for each core, then gradually increasing the Fmax boost override in case the boost frequency is hitting the frequency ceiling. The all-core stability process includes running Prime95 small FFTs with both AVX512 enabled and AVX disabled. The benchmark validation process includes completing all the benchmarks I've included in this guide. If a benchmark is unstable, I increase every core's per core curve optimizer value by 2 steps until I reach stability. In my case, I used an all-core curve optimizer of -25 and an Fmax boost override of +100 MHz. I will show you the BIOS configuration in a minute, but first, please note that the curve optimizer settings are CPU specific, so the optimal values for your CPU may differ substantially from what I'm about to show you. Also note that this CPU is a fantastic overclocker. I've seen some other 16-core CPUs that had trouble running -5 negative curve optimizer. The following table shows the boost profile for this specific CPU. We can make a couple of interesting observations. At stock, we see a story of two totally different CCDs. The cores in CCD0 boost a minimum of 100 MHz higher than the cores in CCD1. Furthermore, only cores 0 and 6 boost beyond the advertised boost limit of 5.7 GHz, whereas the maximum boost frequency of the other cores ranges between 5430 and 5620 MHz. Note that while AMD advertises a boost clock of 5.7 GHz, the actual programmed Fmax frequency ceiling is 5.85 GHz. So, on some CPUs, you may see the frequency boost beyond the advertised boost frequency. In our case, we see Core 6 boost to almost 5.8 GHz. After curve optimizing, we can see a substantial frequency uplift across the board. While none of the cores are hitting the increased Fmax ceiling of 5.95 GHz, all cores in CCD0 boost beyond 5.8 GHz. Also, all cores in CCD1 boost beyond 5.6 GHz. On average, the maximum boost frequency increased from 5537 MHz to 5757 MHz. A quick word on two settings included in the GIGABYTE BIOS. The settings become available when you enable EXPO. The settings are low latency support and high bandwidth support. Unfortunately, I don't know what the settings do exactly, but they positively impact performance in memory-sensitive benchmarks. Enabling the settings may cause instability, so it's up to you to decide and see if your memory is stable when these options are enabled. In my case, I enabled the high bandwidth support option, and I see a positive performance impact in benchmarks like Geekbench 5 Multi and AI Benchmark. Upon entering the BIOS, switch to Advanced mode. Enter the Advanced CPU Settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limit to Motherboard. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override Plus to 100. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to Negative. Set All Core Curve Optimizer magnitude to 25. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Leave the Advanced CPU Settings submenu. Set XMP EXPO High Bandwidth Support to Enabled. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set System Memory Multiplier to 60. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. The performance uplift after curve optimizing is pretty solid. It's nice to see we have achieved better performance across the board, even in single-threaded benchmarks. We see the highest performance improvement of plus 13.90% in Geekbench 5. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4944 MHz with 1.17 volts. The average CPU temperature is 95.3 degrees Celsius. The ambient and water temperature is 27.3 and 39 degrees Celsius, and the average CPU package power is 242.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 5093 MHz with 1.227 volts. The average CPU temperature is 95.2 degrees Celsius. The ambient and water temperature is 25.8 and 37.6 degrees Celsius, and the average CPU package power is 244.2 watts. In our third overclocking strategy, we take advantage of the return of Eclk mode. Eclk stands for External Clock Generator, and it is exactly what the name suggests. It's an external clock generator. This feature was also available on Ryzen 2000 Pinnacle Ridge CPUs, but was removed afterward, until now. The standard Raphael platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. In addition to the standard internal CGPLL, Raphael supports up to two external clock modes. They're called Eclk 0 mode and Eclk 1 mode. In Eclk 0 mode, an external 100 MHz reference clock is used for both the CPU and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks as well as the PCIe and SATA clocks. In Eclk 1 mode, there are two distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. AMD suggests up to 140 MHz can be expected for the CPU core reference clock, but your mileage may vary. In previous SkatterBencher videos, I referred to the process of overclocking the reference clock as supercharging PBO. Unlike previous platforms, support for external clock generator and reference clock overclocking is very good, so it provides us with a viable path for overclocking. The overclocking strategy with Eclk is the polar opposite of what we're used to with Ryzen CPUs. Typically, as shown in OC strategy number 2, Ryzen overclocking consists of using curve optimizer to add a negative voltage offset to the CPU core VFD curve. By doing so, the CPU will boost to higher frequencies. With Eclk, we still build on top of the factory-fused VFD curve, but we adjust the frequency by adjusting the reference clock. For example, if the precision boost has a VFD point for 5 GHz at 1.25 volt at 50 degrees Celsius, with an Eclk of 105 MHz, the actual point will be 5250 MHz at 1.25 volt at 50 degrees Celsius. Obviously, the default voltage for this VFD point won't suffice for stable operation. So, counterintuitively, we use a positive curve optimizer to increase the voltages of the VFD point. For example, a plus 30 curve optimizer may increase the voltage by 150 mV. Thus, the resulting VFD point will be 5250 MHz at 1.4 volt at 50 C. If curve optimizer doesn't provide you with sufficient voltage, you can always add a voltage offset via the VRM controller configuration. One more important point. Eclk also affects the maximum frequency ceiling. With an Eclk of 105 MHz, the new programmed Fmax for the 7950X is 6143 MHz. That's way too high for this CPU. Luckily, we can use a negative Fmax boost override to fix this. The manual tuning process for Eclk can also become quite convoluted since it still spans that entire range from single-threaded light workloads to all-core multi-threaded heavy workloads. The process that I followed for the Eclk tuning is very similar to my curve optimizer process. First, I use a broad tuning approach to get a big picture understanding of the tuning opportunity. Then I narrow down the per core curve optimizer settings to achieve stability in a light workload. Then I verify the stability in all core multi-threaded workloads. Lastly, I run through all my benchmarks to validate stability in a wide range of test scenarios. The broad tuning process includes using SuperPi32M with affinity set to a specific thread to check the maximum effective clock frequency, gradually increasing the reference clock until the point of instability. In case of instability, gradually decreasing the Fmax boost override. The narrow tuning process includes using SuperPi32M with affinity set to a specific thread to check the maximum effective clock frequency, gradually increasing the Fmax boost override in case the boost frequency is hitting the frequency ceiling. In case of instability, gradually increasing the per core positive curve optimizer. The all-core stability process includes running Prime95 small FFTs with both AVX512 enabled and AVX disabled. The benchmark validation process includes completing all the benchmarks I've included in this guide. If a benchmark is unstable, I increase every core's per core curve optimizer value by 2 until I reach stability. In my case, I use an Eclk of 107.75 MHz, an Fmax boost override of -325, and a per core curve optimizer ranging from +10 on cores 4, 6, 8, 9, 10, 11, 12, 13, and 15 to +20 on core 2. I'll show you the BIOS configuration in a minute, but again, please note that these settings, especially the curve optimizer settings, are CPU specific. So Your CPU's optimal settings may be very different from what you're seeing in my BIOS configuration. The following table shows the boost profile for this CPU. We can make a couple of interesting observations. Tuning with Eclk provides slightly lower absolute maximum boost frequencies than when tuning with Curve Optimizer, as Core 6 boosts to only 5864 MHz. However, across all cores, the maximum boost frequency is about 40 MHz higher, and the lowest maximum boost frequency is almost 100 MHz higher. Overall, the Eclk strategy typically provides an avenue to slightly higher frequencies at the cost of slightly higher voltages. While this offers better performance in light workloads, the higher voltages will push the CPU quicker to the thermal limit. Thus, in heavy workloads, strictly using the Curve Optimizer tool for undervolting yields slightly better results. However, it's important to remember that we cannot set an Fmax for the individual cores, so our Fmax limit applies to all cores. Suppose our overclock specific Fmax, determined by the combination of Eclk and Fmax boost override, is too high for one of the cores. In that case, it will result in instability regardless of the capability of the other cores. Upon entering the BIOS, switch to advanced mode. Set CPU clock control to 107.75 MHz. Set async CPU PCIe clock to enabled. Enter the advanced CPU settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to advanced. Set PBO limits to motherboard. Set CPU boost clock override to enabled negative. Set max CPU boost clock override minus to 325. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. For every core, set Curve Optimizer sign to positive. For cores 0, 1, 3, 5, 7, and 14, set Curve Optimizer magnitude to 15. For core 2, set Curve Optimizer magnitude to 20. For cores 4, 6, 8, 9, 10, 11, 12, 13, and 15, set Curve Optimizer magnitude to 10. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Leave the Advanced CPU Settings submenu. Set XMP EXPO High Bandwidth Support to enabled. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set System Memory Multiplier to 60. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. As the maximum boost frequencies have substantially increased beyond the stock values, we can see a performance uplift across the board. Even in single-threaded benchmarks, we see a nice performance improvement. The highest performance increase is plus 14.73% in Geekbench 5. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU effective clock is 4843 MHz with 1.177 volts. The average CPU temperature is 95.3 degrees Celsius. The ambient and water temperature is 26.9 and 38.3 degrees Celsius, and the average CPU package power is 242.6 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 5068 MHz with 1.228 volts. The average CPU temperature is 95.2 degrees Celsius. The ambient and water temperature is 26.2 and 37.4 degrees Celsius, and the average CPU package power is 243.4 watts. In our fourth overclocking strategy, we will pursue a manual overclock. One could question the use case for manually overclocking a Ryzen CPU. Just like with any of the previous Ryzen platforms, the major downside of manually overclocking a Ryzen CPU is that you lose all the precision boost functionality, including those really high 1T frequency boosts and the associated performance. So whereas your CPU, this 7950X, can boost up to 5.85 GHz in precision boost mode, in manual overclocking mode, you will be limited to your fixed set frequency. However, manually overclocking does have some benefits. First, automatic overclocking and frequency boosting technologies leave a little margin on the table. We can exploit this margin and fine-tune it for application and system-specific stability when manually overclocking with our specific hardware configuration. Second, AMD Ryzen CPUs allow setting the frequency for each CCX separately, so we can exploit the fact that some CCXs can be overclocked higher than others. Thirdly, by setting a fixed voltage, we avoid the CPU dynamically and rapidly updating its VID requests to the VRM controller. This alleviates stress on the VRM and typically yields lower temperatures. To better understand the performance tuning opportunities embedded in this Ryzen 9 7950X, let's have a closer look at the voltage and clocking topology. The clocking of AMD Raphael is similar to the previous generation of Zen 3 Vermeer desktop CPUs. The standard Raphael platform has a 48 MHz crystal input to the integrated CG-PLL clock generator. The CG-PLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides CPU clock frequency granularity of 25 MHz. As with Vermeer, each CCX has its own PLL, with the cores within that CCX running at the same frequency. In typical operation, all cores within a CCX will run at the same frequency. However, the effective clock may differ if cores are running in a different P state. The SoC PLLs include a wide range of PLLs present on the I/O die. The most relevant ones for overclocking are Fclock for the data fabric, Uclock for the memory controller, Imclock for the system memory, GFX clock for the integrated graphics. The SoC PLLs are not particularly relevant for manual CPU core overclocking. As we covered in OC strategy number 3, Raphael also supports, in addition to the internal clock generator, 2 external clock generators. However, we won't be using Eclk in this overclocking strategy. From the voltage topology, not much has changed. Similar to Vermeer, Raphael still relies on both internal and external voltage supply to power the CPU. There are 4 primary power supplies from the motherboard VRM to the processor. I have covered the details extensively in my Raphael overclocking launch video. The VDD-CR voltage rail provides the external power for 2 internal voltage regulators, VDD-CR CPU and VDD-CR VDDM. VDD-CR CPU provides the voltage for the CPU cores within the CCX. The voltage rails can either work in regular or bypass mode, but on Raphael, it's always in bypass mode. That means the voltage is always equal to the VDD-CR external voltage. VDD-CR VDDM provides the voltage for the L2, L3 and if present, 3D V cache on the CCX. This rail cannot work in bypass mode, therefore it is internally regulated from the VDD-CR external voltage rail. Choosing an appropriate manual voltage is always going to be a matter of finding a suitable trade-off between increasing the overclocking potential, dealing with any of the thermal challenges that come our way, and of course, CPU lifespan. It's with that last thought that we kick off our manual overclocking process. Our main limiting factor will always be our cooling solution, since power consumption scales exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So, the first step in our tuning process would be deciding on the stress test representing our worst case scenario. In this case, I will pick the 30-minute Cinebench R23 stress test. The next step is to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CCX ratios. Simply increase the CPU ratios until the application shows signs of instability, then back off. This approach will give you the maximum stable per CCX frequency for a given voltage. In our case, we end up with a CPU ratio of 54.25x for CCD0 and 53.75x for CCD1, and a core VID of 1.25 volt. During our stress test, this yields a CPU voltage of 1.285 volt and a CPU temperature of 97 degrees Celsius. Upon entering the BIOS, switch to advanced mode. Set CPU ratio mode to per CCX. Set CCD0 CCX0 ratio to 54.25. Set CCD1 CCX0 ratio to 53.75x. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set XMP EXPO High Bandwidth Support to Enabled. Set System Memory Multiplier to 60. Set CPU vCore to 1.25. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, we see a performance deficit against stock performance in single-threaded applications, as manual overclocking doesn't benefit from the Precision Boost 1T frequency. In multi-threaded applications, however, we see a nice performance uplift up to plus 13.28% in Geekbench 5. When running Prime 95, unfortunately the CPU is not stable. This is a deliberate choice on our side, as we decided to forego stability in extreme scenarios in favor of Cinebench R23 as a stability requirement. In our final overclocking strategy, we rely on Active OC Tuner to bring together the best of Precision Boost Overdrive and manual overclocking. Active OC Tuner, or AOCT for short, is GIGABYTE's way of addressing a fundamental problem with AMD Ryzen CPU overclocking. It was first introduced on the X570S Aorus Master motherboard and has since been implemented on other GIGABYTE motherboards as well. As we already know, there are two ways to overclock an AMD Ryzen CPU: Precision Boost Overdrive and OC mode. Precision Boost Overdrive has the benefit of retaining all the automatic boost algorithms, including the peak single-thread frequency and associated performance. OC mode has the benefit of enabling precise per CCX fine-tuning, enabling the maximum stable all-core frequency. So, you typically have to choose to compromise either the best single-threaded performance or the best multi-threaded performance. GIGABYTE Active OC Tuner provides us with the best of both worlds, allowing us to actively switch between Precision Boost Overdrive and manual OC mode. It's most easy to conceptualize AOCT as benefiting from those really high precision boost frequencies and having a floor frequency in case of all-core workloads. AOCT requires little additional configuration work. We need to know two things. One, what is the lowest frequency we will allow? And two, at which point do we want to switch between PBO and OC mode? Sadly, we cannot just define a minimum frequency and have the system switch based on that. Instead, we need to rely on a proxy metric, a current threshold or a temperature threshold. There's no perfect or ideal way to determine what is the right threshold, so I'll show you one example using Cinebench R23. The first step is to determine your desired manual overclock. In our case, we can rely on our overclocking settings from OC strategy number 4. We can write these settings down and return to the Precision Boost Overdrive mode. The next step is to apply all your Precision Boost Overdrive tuning settings, including any custom curve optimizer or Fmax override settings. In our case, we can rely on the settings from OC strategy number 3. Then go into the operating system and open your stress test tool of choice and hardware info. We aim to find the exact point where the Precision Boost frequency drops below our target manual overclock of 5400 MHz and check the current use. In hardware info, usually, we would monitor the VRM current. Unfortunately, it's not available on this version of the software, so instead we monitor the CPU package power and vCore. Our current value will be the power divided by voltage. Then we start the Cinebench R23 stress test and change the affinity to one thread in Task Manager. Now monitor the core clock frequency. It will be much higher than our target of 5400 MHz. Now you can gradually increase the active thread count. When you reach 5400 MHz or below, check the CPU package power and vCore. In my case, we reached a frequency of 5400 MHz at about 20 active threads. The CPU package power reads 200 watt at a voltage of 1.3 volt. So the current threshold value for active OC tuner will be around 150 amps. So to reiterate what's happening, active OC tuner will actively switch between OC mode and precision boost when the CPU current hits 150 amps. Anything above 150 amps engages manual OC mode. Anything below 150 amps will engage precision boost. Oh, one last thing. Our Precision Boost Overdrive Eclk OC strategy includes an adjusted Eclk frequency of 107.75 MHz. When active OC tuner switches between PBO and OC mode, it does not change these settings. So we must adjust our manual overclock settings accordingly. Upon entering the BIOS, switch to advanced mode. Set CPU clock control to 107.75 MHz. Set async CPU PCIe clock to enabled. Set CPU ratio mode to per CCX. Set CCD0 CCX0 ratio to 50.25. Set CCD1 CCX0 ratio to 49.75. Set active OC tuner to manual. Set CPU current limit to 150. Enter the advanced CPU settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to advanced. Set PBO limits to motherboard. Set CPU boost clock override to enabled negative. Set max CPU boost clock override minus to 325. Enter the curve optimizer submenu. Set curve optimizer to per core. For every core, set curve optimizer sign to positive. For cores 0, 1, 3, 5, 7, and 14, set curve optimizer magnitude to 15. For core 2, set curve optimizer magnitude to 20. For cores 4, 6, 8, 9, 10, 11, 12, 13, and 15, set curve optimizer magnitude to 10. Leave the curve optimizer submenu. Leave the Precision Boost Overdrive submenu. Leave the advanced CPU settings submenu. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set XMP EXPO High Bandwidth Support to enabled. Set CPU Memory Multiplier to 60. Set CPU vCore to 1.25. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, by relying on active OC tuner, we get a performance mix similar to the best results from OC Strategy 3 and number 4. Interestingly, we don't get the outright best performance across all benchmarks. In some scenarios, a tuned precision boost outperforms our manual overclock in an all-core workload. Also, there may be a performance hit when the load is right on the active OC tuner switching point. We see the best performance improvement of plus 13.94% in AI benchmark. Alright, let's wrap this up. The Ryzen 9 7950X is the flagship processor of AMD's Ryzen 7000 product lineup, and it's most definitely the fastest in both advertised frequency and overclock frequency. It's quite satisfying to see an AMD Ryzen CPU boost beyond 5.8 GHz using just regular water cooling. That said, I do think there will be some discussion in media and in the community regarding the big difference between the overclocking and boosting capabilities of the cores within this 16-core CPU. On my particular sample at stock, the difference between the best core and the worst core was about 350 MHz in boost frequency. That difference comes down if you use curve optimizer or Eclk overclocking, but the gap will remain throughout that entire process. I think the gap at my best overclock was still about 190 megahertz. In addition to that, this chip was actually quite a good overclocker. I was able to even see beyond 6 gigahertz on some cores. And not all Ryzen 9 7950X CPUs will be capable of that. I've seen some 16-core CPUs that weren't even able to do -5 curve optimizer. So Silicon Lottery will be quite an important part of your overclocking adventure, at least very early on in the life cycle of these products. Anyway, that's it for today. I want to thank my Patreon supporters for supporting my work, and I want to thank you for watching. If you want to have a look at the written version for my BIOS settings or some of the screenshots, I'll also put that up on my blog. In the coming weeks, I will put out even more Ryzen 7000 overclocking videos, and see you next time.